Hi, today we're gonna make the VST plugin with Juice. Let's run the producer and I'm gonna choose the basic template and give it a name. Let's choose the path to our project folder, which may be a bit confusing if you're gonna choose the whole path to your project. First of all, for those guys who use Git, let's copy the git ignore from Juice SDK to the root folder and modify it. I'll change this line, excluding the only VS user files, and remove all the SDK directories with recommended by the community. And the Juice library code, excluding this file. There we go. I'm about running Visual Studio. For that, I'm switching to Producer and press this icon. Let's rebuild the project, run the standalone plugin and see what's going on. As we discussed in the previous chapter, we need the tape distortion because I want to bring that 18th lo-fi pipe. For that, I'm gonna choose fake distortion method, which tries to implement modulation from low frequencies using vibrator. The standalone plugin shows us the only text, and it makes sense only if we test the audio input from the microphone, which is going through our effect to audio output. That's not super handy, right? To make our life easier, I suggest to run out-of-the-box audio plugin host. To make that real, I'm gonna add the empty C++ project, what I'm gonna set up as the external command launcher. Let's give it a name. Almost forgot that. I have to set the path for the current IDE, and that's not enough. The project was created in the separated folder, that's why I deleted it. Let's move it back where it's supposed to be. Now it's better. Guess what? Yes, I'm returning it back. First of all, it's time to add existing project, not the new one. I'm choosing it in the Explorer and there we go. I'll set it as the startup project, because I'm planning to launch the debugging session with the only key pressed. Let's go to the project properties and in the debugging menu you can choose the command to run. This is my path to audio plugin host. I copy it, type audio plugin host .exe, copy it again, press apply twice, and more of that. I have to change this entry for all the configurations. Now we are ready to discuss the one more interesting thing. As you can see, other projects have an intermediate directory setup. I'm just gonna copy this property to our project and change it according to given name for all the configurations. Great, it seems I'm ready to run the audio host. At this moment we have the empty graph where we can place our VST. For that, I'm gonna edit the list of available plugins and scan for new or updated VSTs. It's quite obvious that we have to remove the old paths and add the path where our VST binary is located. It would be debug folder for now. Contents 8664. Let's do that. Now you can see our plugin in this list. Let's place it and there we go. There is nothing but hello world text inside, and that's all we need to test it out. We need the only sine wave synth and nothing more. Connect them together, and that's it. Both channels and left only. I will save it as is to check if the filter graph was saved. Let's run it again. As you can see, audio plugin host opened the last session. Let's recover it back. Fine, we have handy enough debugging rig. I'm gonna beautify the code a bit. What is some sort of Sisyphean labor, you know? So, I will leave the only time lapse for about 10 seconds. Since I'm pretty sure that I'm gonna create audio effect, I will get rid of preferred channel configuration, its MIDI effect, its synth, and the rest of the preprocessor definitions to keep the codebase dense. You can see that there are a lot of warnings due to unreferenced parameters. The better solution is to comment them out. It will look like more self-documented code. And this is the last one. Yes, channel data was a bit different. Warning. Cool. We don't have warnings yet. Is bus layout supported, maybe optimized a bit? First of all, let's look at the order conjunctive operands inside the condition. How does conjunction work? It will check the next operands only when the earlier will become true. That means it's the better idea to place such arguments which more probably will become false. If we are targeting the music production, I can suppose these probabilities. That means I have to check if it's not the stereo first. But I will go further. Negative equality check works as fast as the positive equality check, but it's quite simpler to read this. But for this trick I have to apply the De Morgan's law. This one should be inside the positive branch. Yep, this one. We have to swap it with the negative one. Let's prettify it a bit. And there we go. But would it be a bit simpler to negate this condition? And now it may be simplified like this. Now we're ready to make the VST. We need the couple of fields for the audio processor. I'm gonna copy sample rate from the prepare to play method's argument from the line number 67 to deal with time-dependent quantities in digital domain. For the same reason, it's crucially important to keep the amount of samples passed, keeping in mind that the value must be overflown after 3 billion years, with the sample rate chosen of 192 kHz. We also need the valued read state, or APVTS. It will bring the serialization and data binding of our parameters for audio, processor, and dependent classes. The bound data will be shown right on the screen and will be sent back after changing the values of the controls as the part of the user interface. Inside the member initializer, I'm gonna keep it zeroed for a while, and the same regarding samples passed field. The visual tree state has more sophisticated constructor. I'm gonna pass the raw reference to this audio processor, but I won't pass the undo manager to keep this task simple. It's quite obviously that identifier should be unique. Let's give it a name operator EPVTS. The last argument is the parameter layout, what might be initialized with the set of audio processor parameters under the hood. We'll use the direct list initializer for that, which I'm gonna keep empty for now. What I'm gonna do is to find get state information method for this class, and since we have value tree state, it's time to implement serialization. Let's get the tree state out of there. Now I can create XML from that. And if we agreed that we do use XML, just unpack it to memory with all the parameters. Destination data should be passed with the name from this time. And let's do the same with the set state information. I'm pretty sure we will need these arguments with their names. This time the task is to create the tree state from the XML, which is given by the binary memory block. It's time to build it for sure. And I'm planning to declare parameters. No warnings there. I'm gonna refer to parameter values from VTS value tree state. Since VTS is valid all the time audio processor exists, I can keep the result of the get raw parameter value, the raw pointer to atomic float. As we are making the fake distortion, I'm gonna evolve the vibrator stages to blend them together and to get that modulated sound from low frequencies. So we need the rating interface for two LFOs, in the hertz and in degrees. The second stage is actually the second oscillator. We also have the parameters which are common for both LFOs. I will call it overall parameters. We need the depth of the effect, what is actually the mix knob. To create the stereo image, I will shift LFOs in time and attenuate this shift, reducing this parameter. Both of them are expressed in percentages. I'm planning to be able to blend LFOs to achieve more unique sound with our effect. In some cases, vibrator exhausts too much energy, so we may need to boost the signal back, expressed as percentage. Inside the direct list initializer, I'll initialize all the parameters via make unique call. There is the identifier, name, minimum, maximum and default value. Let's duplicate them to change the arguments only. The same for the second LFO. Now for the phase 2. This is overall depth. And again boost. Now I'm getting the values through the rope pointer. And as usual, the same for the second LFO. Pay attention to these string identifiers. We will use them and discuss them later. Overall, with LFO blend, and the game boost. The very common question is, what should I do to send data from parameters to user interface? It would be a good question for this stage. When we declare the parameters to work with serialization and UI, we need so-called APVTS or audio processor value tree state. Let's use constructor injection and declare the field audio processor value tree state with this acronym. As the lifetime of tree state is more than the life of the editor, we can use raw C++ reference. The same as the reference for the audio processors being used. Since we have the value tree state, let's declare sliders for our user interface. The same for the second LFO. Overall depth, stereo. Let's blend them together and boost a bit. I'll use type alias for the slider attachment. Which is from value tree state namespace. So what is that? Attachments offer bindings like WinUI or WPF does. This is the last glue between view and the model, with no more boilerplate in there. I wouldn't like to waste your time, guys, so I just copied this editor constructor method body. If you want to investigate this code, welcome to the description to explore the GitHub repo. You can see the parameters bound by the strings, which offer some sort of DI, driven by the named instances. That's why the Juice is very handy SDK. And the same for the resized. They don't do anything interesting here. We just drew the text and set the bounds for our sliders. Let's check it out. I think it looks compact enough. As you can see, it has no chances being resizable. We can fix it adding resize limits. And of course I have to make it resizable also with the corner resizer. Build OK, let's try it again. Now it seems to be better, right? Because we have decent UI in terms of this task, it's time to switch to make this plugin real, which changes auto buffer. I mean, I will bind the parameters one by one to make this process comprehensive enough, but for now we need some measures to prepare the codebase. We'll need the sample rate in our pipeline, thus I copy that at prepare to play stage. From initial sample rate. We have some number of samples in the buffer, so it's a good idea to copy that number. And we can increment these samples passed by this number of samples. I'm gonna replace per channel loops with the logic which is bound to certain channels in the certain buses. The first one is the main input, which is given by the input buffer. Is input is true, bus index is 0. Let's introduce the constants there. This one is true value for getBusBuffer method argument and bus index for the main input, not the sidechain. Now it's time to obtain the number of channels. From the given bus. And relying on this certain number of channels, we will implement the different logic. I will explain why. But for now, it's worth to mention multi-channel case, which will be untouched. That means the buffer won't be changed. Let's declare channel number constants. Mode is 1. Channel indices. Left and right. What is interesting here that I'm gonna process channels separately, relying on the inline expansion of the compiler with no performance impact in the release version of VST. Now the mono. And it's time to declare the process channel dummy with amount of samples and the pointer to the first one. Since some cases can forbid the inline expansion, I'm gonna add the inline specifier, which is rather about the permission. The final result depends on your settings. Now it does nothing. It keeps the buffer the same. How about the boost? First of all, I'm gonna replace constant value with overall boost, which I will get from the parameter, which is called between 1 and 2. I have to inject the new argument. Which should be result of interpolation within 1 and normalize boost. Since we have to keep the value in range 1 and 2, I need to add 1 over the depth, where the overall depth is the 100% of depth parameter. That means we got the normalized value between 0 and 1. We still don't have the loop function, right? Begin of the interval, end of the interval, and alpha. This is the math. While it's building, I'll set the focus on the process channel. Boost is working now. Since we're gonna make the fake distortion, how about implement the core of this effect, the vibrator? All we need is introduce the amp modulator for audio buffer, which should be a lerp result within 2 LFOs. Over 50% for now. Also, I have to lerp the modulator by overall depth. The modulation from every LFO is between 0 and 1, so we need the bias constant with the value of 1.5. P times phi, where phi is the common amount of samples. Divided by vibrator rate. There we go. Let's declare missing arguments. Overall depth from 0 to 1. And the rate in samples. There is the redundant semicolon, definitely. Let's declare the base factor, the bias I mentioned before, with the value of 0.5. And since we changed the method signature, I need to pass the new arguments. It would be a good idea to keep the rate and samples as a constant value of 2400 for a while. And we also need the amount of samples passed. Build and run and listen to the result. Cool. You've noticed that we've built a simple vibrator effect based on the constant values, which is not quite well. Moreover, at now, we have no way to make phases different in different channels. Thus, I'm gonna involve the phase shift in LFO argument. Now, let's pass them. For now, I will declare the phase shift with a constant. Range from minus 0.25 to plus 0.25, minus 90 degrees to plus 90 degrees. The same for the second oscillator. Sounds like a vibrator, but it doesn't offer a serious threat like Ableton Live's Autopun does. For that, I'm gonna declare the enum with the phase shift direction and provide it as an argument for the proto channel. Let's pass the enum values into the cause. To provide the differences in the stereo image, we need to ask the phase shift direction for the every channel and solve the phase shift mount according to that direction. Build and run again. It works, but it's definitely would be better if we had the possibility to control the rate, phase shift and the stereo width without sliders. For that, I copy the value from the atomic parameter. We replace the constant for the phase shift with the angle in the full circles, multiplied by the overall width. Now, rate in samples is given by the sample rate divided by the rate in hertz. Let's copy that. Build and run. Let's try different phase shift values. Now it does nothing. What makes sense, right? Let's also try to use the different frequencies there. Fine. You can notice that the amount of blend keeps the same 50%. Now it's time to involve the LFO blend value. I will add the argument among the other overall values. Now it's okay. I have to pass the blend value in the process channel codes, where LFO blend is the 100th of 0 to 100% value. It's time to check it. Quite well, but you could notice that with the blend value around 50% we have some sort of a mess, right? To get rid of that, I have to multiply LFOs and use the nonlinear interpolation to not to lose too much energy. In other words, if in the previous case we blended 2 LFOs over the blend value, now we have to interpolate the 1.f for the first LFO, then blend the second LFO with the 1.f and then multiply them. To get the equation for the nonlinear interpolation, I'm going to exponentiate the alpha value not to use the load function, which might not be inlined. I can simplify it with the following way, which is actually the same. Now we can use it. The idea is to interpolate each multiplier with 1.f. Let's define the curve power constant. Power of the nonlinear interpolation function to blend LFOs. And I will leave the comment for the previous section also. Let's build and run again. In my opinion, it choppers a lot, but there is the problem. You can notice that the minimum and the maximum values, the sound is too loud. To fix this, we need the blend boost multiplier. Now I have to pass the blend boost values inside the process channel invocations. Blend boost must be results of the linear interpolation between 1.f and the boost itself. Over the depth. To calculate the raw blend boost value, we need this calboost function. Let's implement the calboost method with the target and the blend values in there. But before doing that, let's consider the math behind of this method. Actually, this is the quadratic equation where the parabola goes downside from the boost value till 1 in the range between 0 and 1. Let's try to move this formula in C++. 4 times 1 minus boost times t minus 0.5 squared plus boost. Oops. We definitely have no blend boost variable. Let's build it, and during the build I can add a comment that we have to recover the energy. There we go. It sounds more equal in volume. Let's check it out on the that boring digital code sounding vibe. Now it sounds much warmer like cassette tape does. It brought back that 18th lo-fi vibe in the music. Since we have this soundtrack, in the next chapter we'll integrate the if mode into the clear Unity racing game. See ya.